Hello, everyone, and welcome to the first session of Machine Learning Fundamentals and Introduction to Python course with engineer host Belyadi. My name is Jamila, and I am last year petroleum engineering student at French Azerbaijan University. Today, I'm your moderator for this session. First of all, I would like to introduce our special guest, engineer host Belyadi. He is a senior data scientist engineer at Wine Oil and Gas. Additionally, he is founder and CEO of Observe Intelligence, focused on providing artificial intelligence in-house training and solutions. Mr. Belyadi has served as an adjunct faculty member at multiple universities, including West Virginia University, Marietta College, and St. Francis University. He taught data analytics, natural gas engineering, enhanced oil recovery, and hydraulic fracture stimulation design. Mr. Bilyadi, over 10 years of experience working in various conventional and unconventional reservoirs across the world. He has worked on various machine learning projects and held short courses across various universities, organizations, and the Department of Energy. Mr. Belyadi is a primary author of Hydraulic Fracturing in Unconventional Reservoirs, first and second editions, and is the author of Machine Learning Guide for Oil and Gas using Python. He earned his bachelor's and master's degree both in petroleum and natural gas engineering from West Virginia University. Now I will give short information about course itself. It consists of 4 webinars, each about 1.5 and 2 hours duration. Webinars will be conducted on Saturdays at 7th, 14th, 21st, and 28th November at 9 a.m. Texas time. Participants, of course, will be able to take 4 quizzes, one after each webinar, and final exam in the very end. Successful participants will be provided by certificates. Please don't hesitate to ask your questions to Mr. Belgade regarding today's session in question and answer section. I will read them out in the end. In case of any problem, you can approach me in chat box. And now I ask you to give all your attention to our speaking. Mr. Meliadi, mic is yours.
Thank you so much, Emil. I appreciate it. Thanks to Paya Petro and everybody for organizing this, for Ahmed especially for putting a lot of time and effort into this. I think this is a great program. Everybody else, I'm very excited to be here and talk to you guys about machine learning and Python and what we can do with it. So with that being said, before we get started, if you're interested in listening to podcasts and learning information from the experts, in the field, I have this podcast called Observe Intelligence, where I invite executives and professors from different places to talk about the future of data science and automation. So feel free to subscribe to the channel on YouTube, check the website, and also send me an email through info@observeintelligence.com. And then all the materials that we'll cover in this class will be coming from this book, which will be published early next year. And it goes over pretty much all the fundamentals of machine learning, step-by-step code, and everything else that you need to get started applying and implementing different machine learning algorithms within Python. So with that being said, let's get into and talk about what machine learning is and then get going. So first off, the first question that a lot of people ask is, well, what is machine learning? Let's go over what machine learning is, some of the fundamentals of machine learning, and then over the next few lectures, we'll go in more depth and more detail. And then towards the last couple of lectures, we'll actually, show you how to download Python, how to actually get started. We'll actually go through some coding towards the end of the course, okay? So machine learning, so what is machine learning? So as the volume of data increases, human cognition is no longer able to decipher information from the data, right? So that's when you use some type of machine learning techniques to find pattern, to find information from the data. Let's just say you have, 1,000 wells, okay? And those 1,000 wells each have different design, each have different completions design, drilling design, geologic design, and so on and so forth. You know, if you want to understand pattern or find patterns in the data, it is very hard to look at 1,000 wells and then find patterns, right? Because human cognition can't simply decipher that much information, right? But if you use some type of machine learning algorithm and train a model, then you can understand what is the impact of each, parameter, what is the impact of each input feature on the output feature, which we'll talk about in detail. So one thing that I want you to note here is that machine learning concentrates or focuses on performing specific task. Okay, so we're talking about focusing on a specific task as opposed to data mining, which deals with searching information. So, like for example, a simple example is teaching someone how to play soccer or play basketball. That is machine learning, right? But using someone to find the best soccer centers, the best basketball centers in town, for example, that is called data mining, right? So distinct differences. And one thing that I want you to know is that machine learning, they talk about AI. Well, machine learning is a subset of AI. Machine learning is a subset of artificial intelligence. Okay. So it's just a subset of that. So when they talk, a lot of times they use these terms interchangeably. Okay. So they talk about AI, machine learning, and those things. But just remember that machine learning is a subset of AI, is a subset of artificial intelligence. And then you also hear the term deep learning. This term actually has been used a lot. If you listen to a lot of the executives from Google, Facebook, from Amazon, they all talk about deep learning. And deep learning is simply using an artificial neural network, such as there are different types of artificial neural networks, such as convolutional neural network, recurrent neural network, and so on and so forth. So using those deep learning algorithms, those are called deep learning, and this has gained a lot of popularity in the past few years. When we talk about deep learning, an example is using time series data. When you have time series data, you can use, for example, recurrent neural network, such as LSTM, long short-term memory, algorithm for deep learning. And then you can also use deep learning for image, recognition, text recognition, or even, like for example, an example of using deep learning is using deep learning for seismic interpretation, for fault detection, and you can actually apply deep learning all within Python. They have different packages that we can cover in this class. TensorFlow, Keras, those packages are actually designed for using deep learning. So to summarize this slide, first off, just remember that machine learning is a subset of artificial intelligence, is a subset of AI. That's number one. Teaching someone how to play soccer, play basketball, that's machine learning. Finding the best soccer or basketball centers in town, like for example, is data mining. Okay, distinct differences. Okay, and then deep learning. Deep learning is a subset of machine learning. It's also a subset of artificial neural network, or ANN, which we'll actually talk about in this course. And within deep learning, some of the algorithms within deep learning are convolutional neural network and recurrent neural network. Recurrent neural networks are used for time series analysis, such as there's an algorithm called LSTM, long short-term memory. That's used for recurrent neural network. And for convolutional neural network, that's used for text, image classification, and so on and so on and so forth. So this is just the basic fundamentals of what we're going to talk about. The next thing that I want you to kind of know is hard data versus soft data. Well, what is hard versus soft? Well, hard data refers to field measurements, things that you actually measure in the field. Like, for example, you measure your treating pressure. When you hydraulically fracture a well, you measure your treating pressure, through a transducer. That is hard data, because this is not interpreted. This is not calculated, okay? Proppant type, proppant amount, fluid type, and fluid amount. These are hard data. We know exactly what they are. Surface treating rate. When you hydraulically fracture a well, how fast you're pumping. These are measured again. These are not calculated. So these are called hard data. And then the other kind is called soft data, which are interpreted. You calculate them. Like, for example, if you want to calculate your fracture half length, there are a lot of assumptions that you're making to calculate those fracture half length. Those are considered soft data, okay? Now, there are different techniques. You can use both hard and soft data, but the recommendation is to use as much hard data as possible, because hard data, these are not interpreted, these are not calculated. So the more true data that you use, the better off your model is going to be. So always remember, when you look at, if you have a spreadsheet, okay, if you have 20 columns in that spreadsheet, just classify them. Are these columns hard data or are these soft data? And try to focus on the data that are actually hard data, that are actually measured in the field, that you have like a lot of certainty, a lot of confidence in, as opposed to using soft data. Okay, you can still use soft. I'm not saying don't use soft data, but remember, just to build a solid model that you have a lot of confidence in, try to use as much hard data as possible. So now let's talk about different types of machine learning. There are 3 different types of machine learning. I'm going to talk about each one, okay? And then in the next few lectures, we'll actually build on that and talk about those. So first is called a supervised machine learning model. And they're also called predictive models. And the reason for that is because you're trying to build a model. You have your input features and you have your output feature or features. You could have multiple outputs or you could have one output. So when you have your input features and you have your output feature, or when you have your independent variables and your dependent variables, that is called that's when you can build a supervised machine learning model. Okay, so let's just start with an example in the housing industry, and then we'll go to an example in the oil and gas industry. Okay, so let's just go over the example in the housing industry. So let's just say you want to train a model to predict when a new house comes on the market. And by the way, a lot of these housing companies like Zillow and those guys, they all use supervised machine learning models to build those models. So let's just say you're interested in figuring out, predicting what the price of a house is when that house comes on the market. So you have to look at number of bedrooms, number of bathrooms, how the square footage, does it have a yard? Does it not? Does it have a garage? And so on. And so there are so many variables, right? There are so many variables that affect the price of a house. And by the way, those variables vary from one area to another area, from one country to another country, right? So you have to build a specific model. So now you can, so your input features of the model would be number of bedrooms, number of bathrooms, square footage, and so on and so forth, for all these houses, for thousands and thousands of houses or millions of houses, if you have that much data, right? And the output of the model is going to be what? The output of the model is going to be the price of the house. How much was the price of the house? Was it $100,000, $200,000, $500,000? For each row of data. So you have your input features and you have your output feature in this case. Now you can build a supervised machine learning model, And we'll give some examples, some algorithms that fall under supervised machine learning model. The next, now this was an example in the housing industry, which has no relationship to the oil and gas, right? So now let's talk about the oil and gas industry. So a simple example, let's just talk about completions, then we'll go to drilling. Let's just say you have completion design parameters. You have your just sand per foot, water per foot, cluster spacing, stage spacing, well spacing, all of these features. and you're trying to correlate all of these features to an output feature. Let's just call it EUR, or estimated ultimate recovery per 1,000 feet. Okay, that's your output feature. Now you can build a supervised machine learning model. This is an example in the completion side. What about drilling side? Let's just say you have your weight on bit, your torque, your differential pressure, your RPM, your pump rate, and so on and so forth, right? These are the drilling input features. And you're trying to tie all of these features to an output feature. In this case, let's just say the output feature is rate of penetration, or ROP. So that is, again, you can use a supervised machine learning model or use a supervised machine learning algorithm to train a model. So two different examples, one for completions, one for drilling. Or let's just talk about geology. Let's just say you want to build a geologic model. You want to be able to predict, for example, total organic carbon content. You want to predict TOC. Well, you know the features that affect your TOC. For example, it could be gamma ray, could be, resistivity, and so on and so forth. All those input features that affect your TOC, right? So you have your input features and you have your output feature, right, which is your TOC. Again, this is a supervised machine learning model. So the whole point of this is to train a model. And once your model is trained, then you can actually predict, as a new instance comes in, what is the predicted TOC? What is the predicted rate of penetration on the drilling site? What is the predicted EUR, or estimated ultimate recovery per 1,000 feet, for example, on the reservoir completion site? So you can use these features or these a supervised type of model to train a model. That's number one. The second type is called an unsupervised learning, or unsupervised learning technique. So unsupervised is different. So as I said, in supervised, you have your inputs and you have your output, or your outputs. You could have multiple outputs, okay? In unsupervised, you have set of input features, but you have no output. In other words, your data is not clustered. Your data is not labeled, okay? Your data has no label. When the data has no label, it is considered an unsupervised type of model. So in unsupervised learning techniques, the whole point of that is that you're trying to cluster your data. You're trying to cluster your data into different clusters. That is the whole point of unsupervised machine learning model. An example, let's just go over some examples, some oil and gas related examples. Let's just say you have this much acreage position. I don't know, let's just pick a country. Let's just say, I know we have people from different countries, okay? Let's just say, I'm just gonna pick one. I'm just gonna pick Nigeria. Let's just say you're in Nigeria and you have this much acreage position. And you know the geologic features for every single well in that field, okay? You know your TOC, you know your gamma ray, you know your resistivity, your bulk density, and you're trying to cluster all this data, okay, into different clusters, into different areas. You can use unsupervised learning algorithms, which we'll discuss some of the examples, to divide your data into different regions, different clusters. When you divide your data into different regions or different clusters, it basically means that these clusters are similar to one another. If your unsupervised learning technique tells you that this information falls under cluster 1 and this area falls under cluster 2, it means geologically they have something similar, right? This is just one example of using unsupervised technique in the oil and gas industry. You can use unsupervised, to be honest, for a lot of different applications. It just depends on what you're trying to accomplish. A lot of times you can actually use unsupervised learning techniques to cluster your data. And then once your data is clustered, then you can use that clustered output as the output into your supervised machine learning model. And this is called a semi-supervised model. Let me repeat that. So you can use, let's just say you have a data set that has 500,000 rows, okay? 500,000 rows, and it has 10 columns, okay? This data set has no label, okay? So the first thing that you want to do is use some type of unsupervised learning technique to cluster your data. And assuming you're happy with the way the clustering was done, you're happy with the outcome of that clustering, you can use the output of that clustering as the output into your supervised machine learning model, Because remember, in supervised machine learning model, you had to have your input features and output feature. So you can get your output feature from the unsupervised, and then attach it to as the output feature into your supervised model, and then build a supervised model. And this process is called semi-supervised. Then the last type of algorithm is called reinforcement learning, which actually is gaining a lot of popularity even in the oil and gas industry. So with reinforcement learning, let's just start with a simple example with reinforcement learning. Let's actually go here. I have an example here. So reinforcement learning is a technique that directs action to maximize a reward of an immediate action and those that follow. And what I mean by that, let's just talk about like very basic terms here. Let's just say you have, a lot of you guys are probably too young, but let's just say you have a kid, and you have a kid that is curious, and he's in the kitchen and he's cutting vegetables. Okay, he cuts vegetables and he sees that cutting like the knife can be used for cutting vegetables, right? So that's a positive feedback that he gets, right? And all of a sudden, as he's cutting the vegetables, he cuts himself, right? Accidentally. Now he also learns that knife, not only can it be used for cutting the vegetables, it can also be used, it can also be dangerous and be used to cut yourself, right? So this is called, so in reinforcement learning, it learns from the good behaviors and the bad behaviors. So the model has to see both good behaviors and bad behaviors to train itself on a continual basis, okay? And it works based on the agent and the environment that I just described, just going back to the kid, So just remember that, in reinforcement learning, you're learning both from good behavior and bad behavior, An example of reinforcement learning in the oil and gas industry, for example, if you're trying to optimize your production data, your reinforcement learning has to see your bad production behavior or bad production data, and also it has to see your good production data or good production behavior. So that's just a reinforcement learning, which is the third main type of machine learning. So now let's talk about some of the machine learning applications for supervised, unsupervised, and semi-supervised in different industries. One thing that I forgot to mention is that you can use machine learning for both regression and classification. So what I mean by regression, what is regression and what is classification? So let's just say you're building a supervised model, okay? The output that you have selected for your model is actually a number. That means you're regressing on that number. It's a regression problem. It's a regression model, right? But let's just say in supervised learning, your output could be yes or no, could be true or false, could be a classifier, which means now you're building a classification model. So you can build a supervised regression model or a supervised classification model, depending on what you're trying to accomplish, depending on what the goal is. Remember, machine learning is just technology, is a tool, but you as the petroleum engineer, geologist, you have to understand what you're trying to apply it to. So it's your knowledge, it's your domain expertise who will determine the problem, So as long as you have a clear understanding of what the problem is that you're trying to solve, you can use machine learning for any problem that you have in mind. You just have to try it to see if there's any correlations, if you can build a successful, high accurate model. Okay. So these are just some examples. Regression, we talked about housing price prediction. We talked about, like An example of unsupervised, if you guys go on Facebook, I'm sure you guys all have Facebook. A lot of you guys that live in like in the United States have, Amazon account and all that. You guys always, or even if you search like something on Google, So how do you think these people recommend you new products? Like, how do you think when you go on Facebook and you scroll down, through your news feed, and you all of a sudden pause on a picture or you click on a link, Facebook recognizes that particular topic, it piqued your interest. And that's why you paused on it. That's why you clicked on it. So those guys are constantly collecting your data and understanding what you like, what you don't like. And the reason for that is because they're trying to propose to you things that you like. For example, if you like, let's just say, if you like sports, if you like watching basketball, okay, and every time there's an NBA, highlight, you click on it, right? Facebook will try to propose you more NBA highlights as you go, because those topics are the topics that you're interested in. Actually, if you want to help Facebook, you know what you should do? If you see a topic that is unrelated that you don't like to see anymore, you can click on it and actually just remove it and say this is unrelated. It will actually help their algorithm, So why are they trying to do that? They're trying to get you engaged, to stay on Facebook, to stay on YouTube or whatever social media program that you're going to use for as long as possible. Because the longer you stay in, the more they can market, the more money they can make. Every time you click on an ad, because that piqued your interest, somebody's paying for that ad. Another company is, let's just say if there is a company that is selling, sports gear, okay? When you click on the ad, every ad has a cost per click. What I'm trying to say with all of this stuff is that it is all done via unsupervised machine learning. There are different techniques like a priori algorithm, for example. You can use that to recommend products to customers that like, if you bought this, you should also buy this. If you go on Amazon, if you bought this, you might be also interested in this, So that's how it's a business model. You can use the data for good things. I'm not trying to say these are bad things. These are, they're trying to understand the customer. They're trying to understand the customer behavior. So they propose products that you might be interested in. And if you're not interested in, then you can move on. You don't have to use it. So this is the whole point of going through the example of Facebook or YouTube or Amazon and those guys. It's just they're trying to collect this data because at the end of the day, when any organization collects your data, the motive is profit. They're trying to profit, sell you products. It's just as simple as that. So this is an example of unsupervised learning and semi-supervised. We talked about that. So now let's talk about some of the examples within the oil and gas industry. We've covered some of these examples actually in the book and with detail as far as how you can perform it. So one is completions and well spacing optimization. You can use machine learning for that purpose. You can build supervised learning for that. Another example is type curve clustering. We talked about that. When you have all the geologic features, you can cluster the geologic features into different areas. And you can also include other types of features in addition to geologic features for your clustering. Another example is rate of penetration drilling optimization. Because in drilling, the objective function is to maximize your rate of penetration. If you can maximize your rate of penetration, you're actually, you're doing very well. So you can use machine learning, supervised machine learning, to train a model to maximize your rate of penetration. Another example is liquid loading. You can use unsupervised learning. I'm actually going to go through that example probably in lecture 2 or 3. Plunger, lift, and intermittent optimization. You can use either supervised learning or reinforcement learning for those. Fault detection through seismic data, geologic log or geomechanical log interpretation, or in general log prediction or log analysis. You can all do all of that using machine learning. Faces classification and automation, how to determine your faces and also cluster that data. You can use machine learning for frac chemical optimization. These are just some examples. I can go on and on about these. And all of these goes back to your domain expertise, to what you understand from the data and what you're trying to accomplish, okay? So now we talked about different machine learning types, right? Under each type, let's go over some of the examples under each type, okay? And you probably have heard these like a lot before. You probably have heard of artificial neural network, or ANN, which we talked about, and we said that recurrent neural network and convolutional neural network are a subset of artificial neural network, and those are called deep learning algorithms, which you hear a lot of the executive. If you listen to, for example, some of the Google or Facebook or Amazon executives that talk about AI, they always talk about deep learning because they understand how important it is to their success and how much value it can actually add. So I highly recommend, YouTube is your best friend. There are a lot of good examples on good lectures, or not good lectures, but good just talk or podcasts with a lot of these executives that talk about the importance of these deep learning algorithms. So I highly recommend those. As I said, I also invite other, executives and professors on my podcast to talk about those. And one of these days, I'm going to invite an expert in deep learning to talk more specifically about it within the oil and gas industry, to go in actually more detail. Other examples of supervised learning, you have support vector machine. This is another powerful algorithm you can use for both regression and classification problems. You can use k-nearest neighbor, KNN, again, for both regression and classification problems. You can use tree-based algorithms. A lot of these tree-based algorithms are very powerful, especially for feature ranking. You can use random forest, extra trees, decision trees, gradient boosting, adaptive gradient boosting. These are just some examples on tree-based algorithms where you can under supervised learning techniques. Of course, linear regression is the simplest form, and logistic regression is also very, it could be very powerful. So there are, as you can see, there are different types of supervised machine learning algorithms, and every problem is different. The nature of the problem determines what type of algorithm to choose. And if you're not sure, you got to test different algorithms to see which one provides you the highest accuracy, the highest prediction accuracy, the highest blind set accuracy. And as long as that provides you the highest accuracy, that is what you should be using, okay? But as I said, a lot of time, the nature of the problem will dictate what type of machine learning algorithm to choose from. For example, if you're looking for time series analysis, in your mind, that I got to use deep learning, because some of the algorithms will not work, So always you have to define the problem, what the objective function is, and then tackle the problem with different available algorithms. Examples of unsupervised learning algorithms, which we talked about. As I said, if you remember, unsupervised, you have no label. You're just trying to cluster your data. K-means clustering, very popular. If you look at K-means clustering, I can name you so many companies, so many presentations that I've sat through before that they use K-means clustering very heavily. It's a very powerful algorithm. It's actually very simple. I'm going to walk you through it probably in lecture 2. So very powerful. Hierarchical clustering, another powerful algorithm, very commonly used also. These are not just in the oil and gas. These are algorithms that are used in different industries, and every single algorithm, was developed by a different person over time. And a lot of these algorithms can be very powerful to find pattern, to find information. The next one is called density-based spatial clustering of applications with noise. In other words, let's make it simple, called DB scan. DB scan, another powerful algorithm, very powerful. We might cover it if we have time in the next few lectures. A priori algorithm, we discussed that, talked about how companies propose you products, how companies, propose this product versus that product. Under reinforcement learning, Q learning, you hear a lot about it, just look it up, Q learning, Markov decision process, very, very powerful algorithms under reinforcement learnings. Okay, so I just wanted to give you some perspective on, we talked about supervised learning, unsupervised learning, reinforcement learning, but we didn't talk about what are some of the algorithms, and these are some examples of some of these algorithms. So now this is probably a very important slide because it kind of summarizes the whole thing. So what, we talk about machine learning, right? Let's talk about how you actually build these workflows, how you actually build a machine learning model. There are different steps to do that, right? Step number one is collecting that data, right? So before you can do any kind of analysis, you have to have data. If you don't have data, machine learning is not a good application. It's not a good technology in this case. So you have to have data. If you're trying to accomplish anything, the first question you got to be asking yourself, do I have the data? And the second question is, do I have the right data? Just having data doesn't mean you can solve the problem. You have to have the right data. A lot of times you didn't track the data, or what a lot of companies realize now that, oh shoot, I should have tracked this data many years ago that I've never tracked. So and so you have to go back now and do a lot of manual process to get that data, right? But the advantage that a lot of the newer companies have is that they understand the importance of data. Data is the new oil, believe it or not. It is the new oil. It is so valuable. And you'll see in the next 5 to 10 years, you'll see how much impact you'll have. The company with the most data will be able to successfully be probably the most profitable. And it's just, to me, data is the new oil. And any company that neglects collecting data, neglects having a workflow for that data, neglects having data pipelines, will be in big, big trouble. I can assure you that. In the past, you used to do all kinds of stuff. Now, to make the right decision, to optimize your wells, to optimize your design, you've got to collect your data. You've got to track your data. Just do a simple search. One of the positions that a lot of companies look for is data engineers. Now, data engineers are not the same as data scientists. Usually data engineers, what data engineers do, they, build data pipelines. They bring all the data into one central place called a central data warehouse. That's what data engineers do. And once the data is ready, then they pass along those data to the data scientist. And data scientists will do the machine learning models and all those things that we talked about. So there are two separate roles. One is responsible for getting all this data and putting it all in a format ready for the data scientists to use. So speaking of data, one of the things that a lot of companies are doing now is having a central data warehouse. It is extremely, extremely important to have a central data warehouse. The best way to think about a data warehouse is think about an Excel. You guys, every one of you know what Excel is today, right? Think about a gigantic Excel that has every single data in just that Excel. This is called a central data warehouse, where you can have all of your data in one central place. Of course, within that central data warehouse, you have different tables and everything, but they're all in one place. If anybody calls me today, let's just say we work in the same company, we work for company X, and you call me and say, Haas, I want drilling data. All right, here we go. I'm going to go into the data warehouse. By the way, those data warehouses could be on the cloud, or they could be, not on the cloud. And we'll talk about that in a minute. I can go to the data warehouse and pull that data for you just like that, very quickly, no problems, But if you don't have a central data warehouse, if you don't have all this data coming into one central place, what makes it difficult is access to the data. It is very, very difficult. You have to have a central data warehouse to make the processes more efficient. A lot of times, I, I used to work for a lot of companies in my past life, and you ask for the data. Oh, he had the data on his desktop, and he left the company. Well, great. Well, you just lost the data. You don't have any data anymore. So this is the problem with saving the data on these people's desktop and emails and all that. Make sure if you work for any company, or if you go and work for any company, the first thing you should bring up, make sure they have a central data warehouse. You'll make everybody's life easier. You have quick access to the data. You don't have to spend days or weeks or months collecting data manually. It's just so inefficient. So make sure you have a central data warehouse. So right now, if you ask me, what percentage of the time is spent on collecting data? I always tell you that, right now it's probably 80% collecting and gathering and cleaning all that data. But over time, the idea is to reduce that percentage from 80% to less than 5%. You want to be able to spend most of your time analyzing the machine learning models, understanding the models, optimizing the models, deploying the models. This is what you want to spend your time on. So I'm still on step one because it's very, very important. So data collection, make sure you have a central data warehouse where all your data is stored. That way it makes it much easier to access that data. Very, very important. The next step number 2 and 3, let's talk about it in the next slide. So within step 2 and 3, you have different things that you ought to do. One is data visualization. You first want to go and visualize your data to see what you have, to see what kind of distribution each data has, to see if your data has, outliers, bad data points. You want to remove those from your analysis. Otherwise, your model will be skewed. So data visualization is extremely important. And when I talk about data visualizations, I'm talking about simple plots like distribution plots, box plots, just scatter plots, just to make sure that you don't have any anomalous points. So when you plot your data, the moment you plot your data, you'll determine, for example, my differential pressure in drilling ranges from 100 to 500 psi, but I have one point that says is 10,000 psi. Does that make any sense? Well, probably not, right? So it's probably just an erroneous measurement or erroneous reading. So you have to remove that data. Or let's just say you're doing a completions analysis and all your data falls, okay, my completions design range for proppant per foot ranges from 1,000 pounds of sand per foot to 3,000 pounds per foot. Oops, I have one data point that is actually way outside and it says 10,000 pounds per foot. Has anybody even pumped this much sand before per foot? So you can, it's probably a typo or it's probably something that was erroneously entered. So make sure always, before you do any analysis, any type of machine learning analysis, to visualize the data to make sure everything is good. The third step is called collinearity removal. And in this step, what you do is you remove parameters that are collinear. An example is parameters that are highly correlated. For example, in hydraulic fracturing, usually, not always, usually when you pump more sand per foot, you also pump more water per foot. Again, unless you're doing testing, that's not the case all the time. But if you plot sand per foot versus water per foot, you see a strong correlation between the two, right? You see probably your R square is probably 90% or 90+%. So you want to remove those collinear features, the features that are similar to one another, before you deploy or apply machine learning before you start training a machine learning model. So remove collinear features, because remember, if you have the same information, they provide you the same data, why would you include both parameters if they provide you the same information? Or remove redundant features, okay, that provide you the same information. A lot of times, for example, you can use dimensionality reduction. There are different techniques for dimensionality reduction. One is called, for example, principal component analysis, or they actually call it PCA. You reduce the dimensionality of your features. And instead of having 10 geologic features, you can reduce it down to 1 or 2 or 3, for example, through principal component analysis, which is a type of dimensionality reduction. Okay. Next is feature selection and ranking. So one of the first things that I always recommend people to do is to rank your features, to see from the top to the bottom which features fall at the top and which features fall at the bottom of your tree. For example, you can use different techniques for feature ranking and feature selection. We'll cover random forest in this course. There are other techniques like gradient. We can use gradient boosting. You can use extra trees, which is an extreme version of random forest. There are different techniques that you can use for feature ranking. So what feature ranking basically tells you is that, hey, after you rank your features, the features that fall at the bottom of the tree, those are those don't have much influence on your model output in the case of a supervised machine learning model. In addition, feature ranking is a function of your domain expertise. That's what we'll talk about in the next slide probably here in a minute. It's very important to select these features based on your domain expertise, based on what you think are important features, because you are, for example, if you're trying to solve a production problem and you are a production engineer, you are the expert, you are the domain expert, you understand the problem, you understand how, for example, plunger lift functions, how it works. So in your mind, you understand it, you're the expert. So this should help you determine, include features that based on your domain expertise are important. If you are a geologist and you're trying to, for example, predict TOC or predict geomechanical properties like shear and compression wave travel times, for example, you are the geologist. You understand geology and most likely a little bit of geomechanics. So based on that understanding, based on that domain expertise, you should select the features that are important. Now you might tell me, Haas, I don't know the answer to that question. I don't know which features are important and which features are not. Not a problem. Include every single feature that you can imagine that you think have a possibility, that you think have a potential. Include them all. And then feature rank. And then select the features that are important. What I'm trying to say, I'm not trying to say that you should know the answer every single time. If you tell me that you don't know the answer, that's no problem. Just include all the features that you're unsure of, everything. Do a feature ranking and select the features that are important. Okay? And then before you feed the model into a machine learning model, you want to make sure you normalize or standardize the data. Some of the machine learning algorithms, for example, like if you use artificial neural network, you have to normalize your data. If you don't normalize your data, your result will be erroneous. Okay? And normalizing data simply means changing the features to be between 0 and 1. For example, let's just say you have sand per foot that ranges from 1,000 pounds per foot to 3,000 pounds per foot. And let's just say you have cluster spacing that ranges from 10 feet to 50 feet. Well, if you include both of these features into your neural network model, they're on different scales, right? So your model will be pretty biased. So you have to first normalize your data across all features to be between 0 and 1. And then once they are on the same scale, then you can actually feed it into your machine learning algorithm. Some algorithms, such as decision tree algorithms, such as tree-based algorithms like random forest, extra trees, these do not require any normalization or standardization. If you do it, it probably wouldn't hurt you, but it doesn't require that. So that's why it makes it convenient. Other algorithms that are distance-based algorithms, for example, some of the unsupervised learning algorithms, such as k-means clustering, those require standardization. And standardization, I'll show you the equations in a minute. It basically means standardizing the data to have a mean of 0 and a standard deviation of 1. And I'll show you the equation. It's pretty simple. It's just the input feature minus average divided by standard deviation. I'll show you in a minute. So depending on the type of algorithm that you have, you either normalize, standardize, or you simply don't. It really depends on the type of algorithm that you are using. So now that we cover these steps, let's go back here. So now that your data has been normalized or standardized and is ready to go, now you can apply a machine learning algorithm, which we talked about. There were different types like artificial neural network, support vector machine, it could be anything. It could be deep learning. It could be anything that you're trying to solve, right? Now you apply those algorithms to train a model. And then you evaluate the model to see how the model evaluates, to make sure that the accuracy is high. For example, if you train a model and your R square is 50%, well, that's a problem, right? Because your R square is pretty low. So then you have to go back and figure out, well, am I missing features in this model that could improve the accuracy? Do I need more data? A lot of times you need more data. If you cannot, add more input features and you don't have more data, then it might be very hard, very difficult to solve that problem. Or sometimes it could be that, hey, you need a better, stronger machine learning algorithm. For example, if you were using neural network, maybe decision tree algorithms could potentially give you higher accuracy. Maybe I'm just saying, So you got to evaluate once you train a model. Well, what's the accuracy? If the accuracy is 90%, then try to improve it and improve it as much as possible. But if the accuracy is 50%, there's something fundamentally wrong. That either you don't have enough data, or you don't have enough input features that you should have included in the model. Then you go back to the piece of paper and start, writing. I'm going to write down, okay, here's the problem. Here's what I'm trying to solve. And think about the fundamental of the problem. What are you trying to solve? And think about which features that you have missed or you are missing and you should include, and then try them. It might improve your model, it might not. But, it's all about massaging your data. It's all about using your intuition, using your comprehension of the problem to include features that you did not include before. So let's just say you train your model, and you're happy with the model. The next step is, what I would do is apply a blind set example to see how the model performs. You apply by a blind set, I mean something that the model has never seen before. Okay, let's just say you have 1,000 rows. I'm going to make it simple here. You divide that data between training set and testing set. Let's just say I'm going to use 70% of the data to train the model, and then I'm going to use the remaining 30% to test the model. Okay, training and testing. So I'm going to train the model on the 70% of the data. Then I'm going to apply it to the 30% of the data to see how the model performs, what the accuracy of the model is. Let's just say the accuracy is 95% and you're happy, for example, okay? And you're happy. You're fine about the accuracy, and you want to move on. Before you deploy that model real time, before real-time model deployment. Test that model one last time on blind sets that the model has never seen during training or testing. That's what I call a blind set, a complete blind set. And then evaluate how the model performs. If the model still performs very well, comparable to your testing set, then you are in a pretty good shape. But if the accuracy just falls off, then you have to go back and try to retrain the model, improve your model. Okay? So training set, testing set. Use 70 to 80% for training, or 70 to 90% for training as far as my concern, depending on how much data you have. And then 10 to 30% for testing. And then do one last check prior to model deployment, just to make sure your model is accurate, you are 100% sure, you have all the confidence in your model. Once you're confident, the last step is model deployment. And we'll talk about edge devices, real-time model deployment, edge devices, and all that, those kinds of things, probably in the next lecture. Okay, so we talked about this slide. So here's an example of anomaly detection and collinearity removal. This is from the book that we published, chapter 24, actually last year. We included a machine learning chapter in that particular book, and this is an example that I pulled from there. And you can see here, this is just a pair plot using Python. Actually, I might show you how to create some of these plots on probably lecture 3 or lecture 4. They're very simple to create. These were created using a library called Seaborn. Seaborn is a visualization library in Python. We can go over those very easy, one line of code. You can create all these plots. It's just, Python is just, I love Python. It's just so powerful. So anyway, so going back to this is just plotting each variable versus one another to kind of find, if you zoom in here, again, this is like very big picture that I'm trying to fit in this slide here. But if you zoom in, you can see points that could be anomalous, that you could potentially, question, what's going on with those points, so that's very important. And then the other plot here is a collinearity removal. So collinearity removal, we talked about this, is just removing features that are heavily collinear. So if you look at this plot here, you can see that the heavily collinear features are, for example, our Bach density. See this density here? This is Bach density. And this is your gas content, or your we call gas in place gas content here. So it just basically says that the relationship, the Pearson correlation coefficient between Bach density and gas in place is minus 0.97, which means that these two parameters are very collinear. So do you really need to include both gas in place and Bach density? You can probably remove one of the features, right? So that's what I mean by collinearity removal. It just simply means creating a heat map or a heat map of your Pearson correlation coefficient, and then removing features that have, plus minus absolute value of 90%. So what is Pearson correlation coefficient? Pearson correlation coefficient is simply the covariance between parameter x and parameter y divided by standard deviation of parameter x times standard deviation of parameter y. So the numbers that you see inside each squared box here is simply the Pearson correlation coefficient between each of these two features. So it just basically says that remove features that are heavily collinear. In this case, as we know, lower Bach density means higher gas in place, and that's why you see this negative 0.97 here. So this is just one example of using Pearson correlation coefficient to remove collinear features prior to feeding it into your model. I talked about normalization and standardization, and these are the equations for your reference. So nowadays you can use the Python library to do normalization and standardization with a couple of lines of code. But the equation is actually fairly simple. I mean, we're talking about, taking x minus the minimum of that parameter divided by max minus min, and that would give you the feature normals. That would give you the like a range of value between 0 and 1. That's called feature normalization. Feature standardization is simply x minus your mean of that data set, the average of that data set, divided by the standard deviation of that column that you're trying to standardize. So as I said, some algorithms require normalization, some require standardization, some algorithms simply do not require neither normalization nor standardization. So the key to success, let's talk about the key to success in machine learning is that you have to combine domain expertise and statistics. As I said, if you're trying to solve a problem, make sure that your organization combines the data scientists that don't have much domain experts or expertise with statisticians or people that have a heavy statistics background to solve a problem. The biggest mistake that a lot of companies will do, and that a lot of companies have done in the past, is that they hire data scientists with higher level education degrees, which there's nothing wrong with that, and do not combine those guys with the domain experts and ask them to solve complex problems. Remember, those data scientists are smart guys. They're very smart, but if they did not have any practical knowledge, practical understanding of how the oil and gas industry works, how a lot of these things work, it'd be very hard for them to come up with something meaningful. That's why it is very important. The key to success in any machine learning project is when you combine the domain experts and the data scientists or statisticians to come up with a good result. So if you are an organization and you are, let's just say, a production engineer, or you are a drilling engineer, you are the domain expert. You understand the problem. You need to be combined with a data scientist or a statistician to use machine learning to solve a problem. Unless you want to just do it all yourself and you're learning and all that, but make sure, when you first start, ask a lot of questions. Make sure you understand the algorithms. Make sure you understand how to code and all those things prior to jumping in. But the key to success is combine the domain experts and statisticians. And I cannot emphasize the importance of doing that. I talked about this data collection and integration, data cleaning, and outlier. Remember, I said you got to make sure your data is cleaned. All the outliers have been removed. Having bad data can break your model. You can use visualization libraries, which we'll talk about in Python, such as Seaborn, Matplotlib. Plotly is an interactive visualization library in Python. Very powerful to just plot simple plots, distribution plot, box plots, heat maps, all those things to make sure that you understand the data. Okay, and also investigate the anomalous points, investigate the validity of these points. And if you're unsure of the validity, just to be safe, you can remove those points from your analysis before, having those points included, which could potentially impact your model's performance and accuracy. So now let's talk about data center. I'm going to talk about data centers in the next few slides, okay? And then we'll wrap it up for today's lecture. So this is very important because you probably hear data centers all the time. Okay. And so what is a data center? A data center simply houses servers and data storage for an organization. So you can have, inside a data center, if you've ever been inside a data center, but by the way, if you haven't been inside a data center, I would highly encourage you to do so. It's basically like a space that you can either rent from Amazon, or you can either, just use Amazon or some of these big providers, just use them, or you can just rent a space yourself and have your own hardware in those spaces. So inside a data center, there are hardware, the space where the hardware is housed, the power and backup systems, environmental controls, and anything needed to keep those servers running. That's what you have inside a data center. So you could have single server or hundreds of servers. Okay. So companies such as Amazon, Microsoft, Google, etc., that offer public cloud computing have cloud data centers that are available to various organizations. So if you look at, for example, Amazon, they have AWS. AWS is a massive cloud data center that Amazon has built. It's very powerful. If you haven't done so, I think they even have some free subscription for people to use. If you haven't done so, check it out. Very powerful. So companies such as Amazon, they have their cloud data center through AWS. Microsoft, they have their cloud data center through Azure, Azure, Azure. That's Microsoft's Azure cloud computing and data center. Google also has their own data centers. So basically, think of a data center as a facility that has all the hardware, all the power and backup systems, and anything related to keep those servers running. And here's an example. This is the picture that I pulled from this website here. You can see this is a picture inside Amazon's data center. Very sophisticated, very powerful. Okay, so that's where a lot of companies, for example, rent these places or through Amazon, through Microsoft, to store their data. And to be honest with you, even some of the very, very confidential governmental information, such as even Pentagon, could be using these data centers, to store their data. So the security is very high. I'm not saying that there could never be a security breach. In today's day and age, the security is a big problem across even companies as big as Amazon. But remember, this is more than $1 trillion company that have a lot of resources and a lot of capital invested in this to make sure the security is very high. So this is just an example of that. So you have different types of data centers. You have cloud data centers, which are, I told you, just Amazon, Microsoft. They have their cloud data centers. And there are on-premise data centers. Let's just say you say, Haas, I don't want to use Amazon. I don't want to use Microsoft. I want to have my own, data center. I want to buy my own hardware. I want to put everything together myself. And I'm going to tell you, no problem. You can do that. So those are called on-premise data centers. On-premise data center, or they call it on-prem data centers. And basically, on-prem data centers are owned and managed by the organization in question for their own internal uses. They don't go to Amazon, or they don't go to, for example, Microsoft or Google. They just want to have, these are usually smaller companies that want to have their own data centers. Okay. So, let me just give you a simple example. The best way to think about it is, let's just say you want to buy, you're contemplating whether you should buy a house or rent an apartment. There are two options. You can rent an apartment or buy a house. So the best way to think about the on-prem data center is that you are buying a house, because you have to, when you buy a house, if something breaks down, you have to maintain it, right? If your dishwasher breaks down, or if your dishwasher breaks down, you have to actually, fix it or call a handyman to come and fix it for you, right? So anything that breaks down within a on-prem data center, you're responsible for fixing it and maintaining it and going through the updates and all those things. But let's just say, Haas, I don't want to deal with all this, you know, uh, owning a house and taking care of this, taking care of that. If something breaks down, I just want to rent a place and, do what I want to do and not worry about all this stuff. Great. That's when Amazon, Microsoft, all those guys come in. You can rent, there's not much, you can like get up to speed much faster. They have everything set up for you. They have data centers. Amazon and those guys have data centers across the world. They have a lot of locations, very secure. Security is high. I don't get money from Amazon to advertise them, but I'm just giving you what I know about them, but I'm not saying that there's not going to be a security breach. That's, it could happen to anybody. But I'm just saying that, you can always, renting a space is like having, going to Amazon and using their cloud data center, or going to Microsoft Azure and using their cloud data centers. Okay. So there's a difference between the data centers, the cloud data centers owned by Amazon, Microsoft, Google, and so on and so forth, and on-premises data centers that you can actually manage and control. You might say, Haas, I want to own a house. Actually, I want to own a house, and also I want to rent an apartment. You can own a house and, I don't know, rent it out to somebody else, or you can rent an apartment yourself, for example. This is the equivalent of, hybrid clouds, So a lot of companies have both. They have, the cloud data centers, through Amazon and Microsoft. And also they have, a traditional, on-prem data center. So they have both, and it's suitable for large organizations. Actually, as a matter of fact, a lot of the large organizations have both cloud data center and their own data center, just as a backup, and there's nothing wrong with that. And this is called a hybrid. So 3 types that we discussed so far: cloud data center, on-prem data center, and the hybrid data center. 3 types. Okay. And to summarize it for you and wrap it up today's lecture, let's look at this. You have the traditional data center, you have the cloud computing, cloud data center, and the hybrid cloud data centers. And you can see here the advantages, disadvantages, and what they're good for. Now you can see, for example, in traditional data center, which is the on-prem data center that we talked about, you have complete control over hardware. Because you're buying the hardware. And by the way, with these traditional data centers, there's an initial investment involved. Buying the initial hardware and all those things to get it all set up, it costs money. So you have to have, an IT budget for that. And if your company is way too small, you don't have the IT budget, you should either get the budget, or if you can't, simply you might just go the cloud route. I'm not saying what's good for your organization. I'm just showing you different types so you're aware of what's going on. Cost of use is easier to understand in these traditional data centers. Privacy can be maintained because you're in charge of your privacy. But again, scammers and phishers could come after you. Even if you're not a huge organization, they could come after anybody. There are so many security attacks these days that go after, small, medium, large size companies. Actually, a lot of these phishing people, they might actually attack the smaller companies because they know it's easier to get into their data. Their security, their IT budget is not high enough, and they know they could get into those like systems. So it is. I mean, if you look at right now, if you look at security, IT security, it's a huge, huge job. Companies are looking for those left and right because of all this stuff that is going on. Disadvantages: you have high upfront costs. You have to invest the capital costs upfront, which costs money. So as I said, you have to have IT budget. It takes up space, uses power, whether used or not. So if you have a traditional data center, it's going to take up space. As I said, you have to have the space, and also you have to pay for power, whether you use it or not. And then it requires a dedicated team to maintain, hard to access remotely. Security is solely dependent on local team. Updates are not automatic. Again, rely on local teams. So your local IT team is going to be pretty busy because they're going to be responsible for maintaining these on-prem or traditional data centers. Okay. And then again, this is good for a small organization that already have a heavy capital investment in IT, or this also is good for organizations that need to be excessively cautious about data privacy. As I said, the cloud is also even if you're cautious about your data privacy, there are still some challenges, I think, that you could face. But this is just good for those companies. Cloud computing, as I said, you have little upfront cost. As opposed to owning these hardwares and everything else, you have little upfront cost. It's a scalable model. That's why a lot of companies love it. Pay for what is used. Like Amazon says, hey, if you're not going to run machine learning models on my servers, you're not going to pay for it. The only time you're paying for it is when you're using it. It's like a simple example that I can give you. I live in Dallas, Texas. Okay. We have tollways here. You can avoid the tolls. You can go around the tolls and drive 10 extra minutes. Or you can take the toll and get your destination, much faster, right? You'd only pay for the tolls when you use them. Same thing here. You only pay for the cloud when you use them. If you don't use them, you don't pay anything. And that's why a lot of companies love it. They're like, why do I have these data centers that I'm paying all this money for when I'm barely maybe using it sometimes, So it's like an on-demand thing. It's like an on-demand process, which is a brilliant business model, by the way. Rapid implementation, easy to access remotely, independent platform, automatically updated, and so on and so forth. It's less control. So remember, this is if you're doing the cloud computing and cloud data centers, you have less control over the actual hardware and operating system. Services and cost structures can be hard to understand at times. I think over time, a lot of these companies will probably simplify their costs a little bit more. But usually they'll send you a subscription. It's based on a subscription fee like model. And this cloud computing, to be honest with you, is good for most organizations of any size. As I said, hybrid cloud, this is a combination of traditional or on-prem and cloud, which a lot of companies do have. It's an opportunity. If you don't want to go completely try out the cloud, you can. It's an opportunity to try out the cloud without a full commitment. So you can do both the combination of cloud and the on-prem. All benefits of a cloud platform are available for use. Cloud can serve as a backup for on-prem data centers. So it's just a backup system that you could have. And then can operate behind a firewall, good for added security, allows more control over some parts of the cloud. Then finally, disadvantages: keeping track of multiple clouds can be tricky, might require a third-party dashboard. So it's just, as you have more data centers, as you have more places, it gets more cumbersome, right? So you just got to keep that in mind. And it's also good for larger organizations with existing IT infrastructure, but who also want to start their own cloud journey. So with that being said, ladies and gentlemen, thank you so much for listening. If you have any questions, I'll take any questions.
Thank you, Mr. Belyadi, for such a wonderful and informative session. And I have several questions to you from the audience. The first one is which software is needed to install?
Which software you guys need to install for this course? Is that what it's asking? Yeah,
Yes.
if you're trying to install, um, we'll walk you through this, but check out Anaconda. Anaconda is a Python, is basically a package that has all the Python libraries already installed, or the majority of pipeline libraries have already been installed on there. So download the Anaconda version, and we can walk you through this probably next class, towards the end of the class. That way, when we start using it, the third or fourth the third or the fourth class, you'll have access to it. And I can also send you guys instructions on that to be more precise. Okay. Next question.
Okay, the next question was about how can we get PDF of this lecture?
Yeah, I can send you guys a PDF copy of this today. Sure. I'll send it to Dr.
And the last question is
Yeah, go ahead. I'm sorry.
okay, how many different clouds there is?
Yeah, so the main one, I think that there are multiple, but the main cloud data centers are, as I said, that are heavily used across a lot of the organizations are Amazon through their AWS. You have Microsoft through their Azure, okay, and then you have Google also has their own cloud data infrastructure. These are the main ones, and there are, of course, other types, but the ones that a lot of organizations trust the most are these three. With the main one being Amazon. That, of course, there's always competition between Amazon and Microsoft and those guys.
Okay, the other question is where can we get the data to practice or develop our models?
Yeah, so in the book that we're publishing early next year, we have placed a lot of the data and a lot of the practice codes and examples. They're going to be all within that book, and also we're going to place it on a link, on an Elsevier link, that you guys can all have access to and practice. And all those data sets are, oil and gas, practical oil and gas data sets.
And this question was more about tackled problems such as RP prediction, and also is this data for
I'm sorry, can you repeat the question one more time?
free? Is data out there
So this,
for free?
as I said, if you're a student in school, you can get the book through Science Direct, through the library. I think if you're a student, it could be free, but I'm not sure. But yeah, once you have the book, whether you get it through your library or whatever, or any other place, once you have the book, you also have access to the links where you have all the codes and data and everything else.
Okay, among the clouds, which cloud you can recommend to us for our activity?
Yeah, I think if you're going to start off, I would start off with either AWS or Azure. But for this class, here's the thing: unless you're going to be running a lot of gigabytes of data, unless you're going to train a machine learning model with gigabytes of data, you don't need the cloud to run your model. You can just use your CPUs or your GPU of your desktop to run those models. If you're going to use very heavy data sets with millions of rows of data, then I would recommend getting into AWS, Azure, and those guys. But unless if you're gonna use an Excel file that has 200,000 rows of data, your computer can handle that. Python that you install on your machine can handle that. You don't need to go to AWS and those guys. But if you're gonna run heavy models, heavy machines, then you got to go to the cloud.
Okay, the next question is, once you have your algorithm validated with R square above 90% and it's working as expected, is there more we can do? And can we optimize the algorithms to use in our models?
Yes, that's a great question. So first off, 90% is not an exact number that I gave and I recommended. First off, you should look at R square, you should look at mean square error, root mean square error. There are different metrics that we haven't even talked about in this lecture. You should look at all the combination of all those parameters to evaluate your model. But to optimize your model, there's a process called grid search. And what grid search does, which again we didn't talk about in this class, is it goes through, because every single machine learning model has a certain hyperparameters, and changing those hyperparameters will also change the accuracy of your model. And a lot of times it's very cumbersome to manually change those hyperparameters and see the result. So what grid search does, it goes through running nested for loops of those different combinations of different parameters to optimize the hyperparameters within that machine learning model. And then there are actually some libraries in Python that you could use to actually do the grid search for you. You just run the grid search with predefined hyperparameters, and then you let it run for overnight or for days, depending on how big how big your data is, and then it will give you the set of optimum parameters, the set of optimum hyperparameters that yields the maximum R square. So that's called a grid search optimization. And then once you're done with grid search optimization, you're happy with your model, you can also use other types of optimization algorithms, which we actually heavily discuss in the book. Some of them are called genetic algorithms, particle swarm optimizations. You can use those optimization algorithms to find a set of features, set of parameters that would maximize your objective function, which you define. That objective function could be your EUR, your MPV, or anything else that you have in mind. But that's a good question.
Okay, also, can we use Google Code Lab?
Can you Google, I'm sorry, Code Lab, what?
Yes, Google Code Lab.
What's the question here?
The question was just, can we use Google Code Lab?
I'm not sure. Honestly, I'm not sure what they mean by that. They can specify more, or just the person who asked that question, just send me an email on info@objectintelligence.com, and I can answer that question. You just provide more information, so I know what you're trying to go.
Okay, maybe this person will write right now. Yeah, someone said maybe he means VS code.
I see. Yeah, just tell them to send me more information to know exactly what they mean.
Okay. There are no more questions for the moment. Thank you, Mr. Belyadi, for the answers. But before leaving, I have an important information to each participant. Don't forget to take your quiz after the session on Google Classroom. That will be available over some time. Also, don't forget to subscribe on PyPetter YouTube channel to watch and recap recordings of today's and all other past sessions. and follow Arab Oil and Gas Academy Facebook page to see and not to miss all details about this and other upcoming courses. And you may also ask your questions there. So there are no more questions. I think we can stop.
Awesome. Thank you so much. Thanks, everybody.
Thank you, good luck, and bye.